So it's a pleasure to introduce our first speaker, who's Omar Sanusi, who will talk about emergent supersymmetry at the critical point of Yukawa systems. Thanks, Omar.
Thank you, Jean, for the introduction, and thanks to the organizers. Can you confirm that you're hearing my voice well, please?
I hear you well.
Okay.
Perfectly, yeah.
Yeah, so emergent supersymmetry. Before diving into the topic, I was thinking about showing you what we are missing from not being in Trento at the moment. So this is a nice picture from the top of the town, and I believe that the institute is somewhere located here, even though I'm not entirely sure. Again, before beginning the talk, I have a few disclaimers. The first one is that my minuscule contribution to the topic dates back to 2017, and it was with Olger and Andreas. And here I'm adding some unpublished material from the years after. And I haven't been publishing much. I haven't been publishing on the topic actually during those years. But luckily, I have some revived interest. Let's say thanks to the appearance of a student that is also among those giving a poster in the poster session. Now, the topic of emergent supersymmetry has been mentioned a few times already during the conference, I believe 3 or 4. My perspective on the topic is mostly based on field theory and RG, which is my main expertise, with a little bit of CFT sprinkled in, if you want. My knowledge of the topic of emergent supersymmetry is very incomplete, to say the least. So in the interest of not making a fool of myself, I refer you to the experts, and in particular, during the conference, we already had 2 nice talks, which were at least in part based on the topic of emergent supersymmetry. And well, there is some additional information. We are currently in the middle of a heat wave, so I might keep the window open, but Italy is also known as the country of noisy Vespas, so please be patient if you hear some noise. So with these things out of the way, let me go straight into the introduction of what the topic is. So I was thinking about, even though I'm not really qualified for this, I was thinking about giving a crash course on supersymmetry. And the crash course on supersymmetry always starts in the following way. We quote the Coleman-Mandula theorem, which essentially states that space-time and internal symmetries cannot be combined in a non-trivial way. So you generally expect in a quantum field theory to have Poincare symmetry times an internal symmetry group. So this is a very famous no-go theorem. But as all theorems, it has a lot of assumptions that you can break. And the simplest one that you could break is that you can think at non-bosonic generators. And few such non-bosonic generators could be the generators that I'm displaying as Q, which you can imagine as the square root of translations. They have anti-commutation relations instead of commutation relations, and their square, in a sense, is the translation operator P. And so these breaking assumptions were later, let's say, more precisely identified in another theorem, which essentially showed that this construction is unique to some extent, and that you can have a certain number, which I'm denoting as n SUSY, of generators like this. Now, why do we call it supersymmetry? The second part of the crash course is the following. So these fermionic generators, essentially what they're doing, they're acting on bosonic states and giving you fermionic states, and vice versa. So if they act on fermionic states, they give you bosonic states. And so these boson and fermion states are actually related, and the entity that is relating them is known as the superfield. So a superfield is essentially a field whose coordinates are in superspace. So it's not only bosonic coordinates, you also have theta and theta bar fermionic like coordinates. And it is the object that I'm displaying in the center. It has a few components. The first one is a scalar field. The second one, psi, is a fermionic field. And then there is an F field, which I will be touching on a little bit more later. And in supersymmetric theories, if you can work on this superspace formalism, you can think that several things are actually the same as in traditional fields, in traditional field theories. And one exception is that you generally substitute, so you work, instead of working with a potential for a scalar field, for example, which is the U that you see below, you replace it with a superpotential that lives in superspace, which is the W. We will see these things a little bit better later on. So the question is, why SUSY? And it's a question that is oftentimes, at least not in condensed matter conferences, this question is oftentimes addressed from the point of view of particle physics. So let me address it from the point of view of particle physics. The development of SUSY was driven essentially by a period of mathematical success of particle physics and QFT in general. And it was proposed as a solution of problems, for example, the hierarchy problem in the standard model. And it's also interesting because supersymmetry plays well with other parts of theory, particle physics theory, for example, grand unification or string theory, the proposed theory of everything. Now, the downsides are that by construction, supersymmetry doubles the numbers of degrees of freedom. I told you that for every boson there is a fermion, no, through the action of the generator. And another downside, between commas, is that there is no evidence of supersymmetry. And now more than ever, and there is even less evidence of strings which need supersymmetry. So the state of supersymmetry for particle physics is now dubious. And while doing research for this talk, I was finding, I was looking for a talk that I've seen some time ago, which now looks like forever ago now, after coronavirus. And the talk was by Licken at this conference, whose title was, Is Supersymmetry Alive and Well? And I think the snapshot that I'm giving you here is, well, there is an horror movie vibe and an horrific font, actually, but let's forget about them. So the snapshot on the right, I think it summarizes the status of SUSY for particle physics well. So there is a first talk and a second talk, which have very different perspectives on how to answer the question of the title of the conference. But sandwiched in between these two talks, there is a glimpse of the talk of this, of the topic of this talk, which is emergent supersymmetry. Now, so seriously, why SUSY? And this is my personal answer. For me, it is still theoretically interesting to try to evade no-go theorems in general. And what I'm gonna try to show you from my simplified field theorist perspective is that there can be low-dimensional condensed matter systems with tunable parameters which can show supersymmetry as an emergent symmetry. And so it is realistic to be able to observe supersymmetry in the lab, maybe not as we originally thought. So let me go to the field theory side, at least for a little bit. And the field theory side has a GRONEVE-YUKAWA model. I'm just referring to it as a Yukawa model from now on. So this model has a real scalar and a Majorana field psi, and the interaction is what you would expect. So there is a self-interaction of the scalar, the potential U, and the Yukawa-like interaction. Now, if you prefer to see things from the perturbatively renormalized side, so this is a theory which is perturbatively renormalizable in 4 minus epsilon dimensions if the potential and the Yukawa function are expanded in that way. So lambda would be the 5 to the 4 interaction and y would be the Yukawa coupling. And this is useful for later on. It is possible to protect the theory from the generation of, so you can essentially engineer a sort of parity in the system. For example, in d equal to 3, you can flip one of the coordinates and transform the fields in this way. And the action that I was showing you above, for example, for these specific choices of U and H is actually invariant. Now, I want to move to supersymmetry to explain you what it is in practice. So suppose that the potential and the Yukawa function satisfy these relations. So essentially the potential is the square of the first derivative of another function, W, which is going to be the spoiler, the superpotential. And the Yukawa function is the second derivative of the same function. So let's plug them in. The Yukawa action is now a supersymmetric action. Why is that? Because it is invariant under these transformations. No, the field, the scalar field transforms with a fermionic parameter into the Majorana field, and also the Majorana field transforms in that way. And this model, the supersymmetric model, is perturbatively renormalizable, similarly to the Yukawa model in 4 minus epsilon dimensions, if the potential, the superpotential W is cubic. Now, what you should have noticed is that the supersymmetry transformation for the Weil field is nonlinear. So if you plug in, for example, the cubic superpotential, then the supersymmetric transformation for the Weil field is quadratic in the scalar field. So one useful step to do at this stage is to introduce a new field, F, which is a scalar, which is an auxiliary field. And essentially, it allows me to break the potential term, which is W prime square, to break it into a term linear and a term quadratic in F. So if you integrate away the auxiliary field F, you're back into the action that I was showing you before. But this time around, the transformations or the supersymmetric transformations become linear. Okay, so I'm transforming also the field F, and instead of having the nonlinear term, which was W prime square in the transformation of the Weil field, is now linear in F, because F has precisely W prime, F equal to W prime are the equations of motion. So now everything is linear, and we refer to this transformation as off-shell supersymmetry transformation. Now with the F field, we can actually do a little bit more rewriting of the action. You can combine all the fields together into the superfield that I was mentioning a few slides back, and using super covariant derivatives, which are, if you want, a generalization of covariant derivatives to superspace. You can write an action in superspace, which, as I promised, has a superpotential W instead of a potential describing the self-interactions of the superfield. And the supercovariant derivatives essentially offer an explicit differential realization of the supersymmetric generators. You can check that they behave in the same way. What is the general idea behind the emergence of supersymmetry? So we know, a lot of us worked on on Yukawa systems that we know that Yukawa systems typically can have critical points as a function of the number of scalars and the number of fermions. So the supersymmetric model you can think of modulo the F field. You can think of as a Yukawa model with a special number of scalars and fermions. In this case, the two numbers are the same. And so you can think that if the critical point, so if the supersymmetric, if the Yukawa model has a critical point and the number of degrees of freedom is the correct one, then this critical point can have a supersymmetry. Okay. Now, a crucial question is in this type of models are how many parameters you must tune to get to criticality. And another crucial question, which is more practical, is how do you construct Weil fermions for these models? Because the construction that I was showing you before needs Weil fermions, so you need Weil fermions in the real world. And I was also briefly mentioning that there are similar considerations that can be done for another Yukawa model in which you have more supersymmetry and specifically twice as many supersymmetries, but we are going to concentrate on the model that I was showing you in the previous slides. So let me try to review, limited my capabilities, what are the proposed realizations. Now, the very first one comes from more than 30 years ago and is mostly guessed on the basis of conformal field theory. And I'm quoting it here because it's useful later on. So if you are in 2 dimensions, you can give a representation of the conformal algebra and also a representation of the superconformal algebra. And these representations have a certain number of labels, okay? One of the most important ones is the central charge, which kind of uniquely characterizes the representation that you have in your hands. And what happens is that the 2 representations, so non-supersymmetric and supersymmetric, share one specific value of the central charge. The central charge counts an effective number of degrees of freedom. And the value that they share is 7/10. And the specific model from the non-supersymmetric side is known through the work of Zamolodchikov to be related to the tricritical easing model. So the question is now, does the tricritical easing model have supersymmetry? And the answer in the original proposal was essentially yes. Now, from a lattice point of view, you can describe the easing model the tricritical easing model as an easing model with vacancies. So some sites are non-magnetic, and the action, as you can imagine, is similar to the one of the easing, but you also have a term which takes into account these non-magnetic parts. And the specifics of the realizations as suggested by Key was that the Weil field, the spinor psi, should come as the disorder operator. Actually, it's a combination of the disorder operator and the magnetization operator if you change specifically the boundary conditions of the model. Because what I should have told you is that the representations of conformal and superconformal field theories essentially are giving you what are the labels of the theory, but are not telling you how these labels are assembled together. It's like when you give a representation of the Lorentz group, you obtain a vector, but this does not tell you what is the action of this vector. So the specifics of the proposal was that they should have we should have studied a mixture of helium-4 and helium-3 at the critical concentration, which is essentially setting the parameter delta in the Hamiltonian to the critical value. But unfortunately, there is no conclusive observation of supersymmetry on this side, on these proposals. And also, one unfortunate thing is that this proposal works only in D equal to 2. I mean, it's very Flatland for several reasons. If you have read the novel, there are also interesting boundary conditions in the world of Flatland. But unfortunately, there's no observation on this side. So more recently, there were a few more proposals. The one that got me interested into the topic was the one by Grover and collaborators. And in this specific case, I mean, I don't want to go into the details also because I'm not an expert on it. In this specific case, Weil spinors are produced at the boundary between two, let's say, parts of the superconductor, which are in two different states. And at this boundary, you can have Weil spinors, which are non-local if you want from the point of view of the bulk, but they are Weil spinors on the boundary. And so they were picking up this action, which is also similar to the Ising model if you want, but it has a Yukawa-like interaction between the Weil and the Weil spinors and the scalar order parameter on the bulk. And they were performing the EMERGECE simulations and computing the central charge. And sure enough, if you tune the magnetic field correctly, you notice that the central charge goes to 7/10, which is a signature of emergent supersymmetry. The 7/10 is separated between a gapped phase and an Ising phase, which have respectively 0 and 1/2 central charge. A very similar proposal, which I will also not go into details of, is the one by Affleck and collaborators. This has already been mentioned during the conference. And this is the Hamiltonian, at least the starting point. And the difference from the previous proposal is that in this case, the evidence for the supersymmetry, which is again central charge 7/10 and so on, is seen not through the Yukawa-like interaction, but there is a 4-Weil interaction, which obviously requires involving 4 sites of this Hamiltonian. So there are proposals, and I take these proposals as an excuse to go back to field theory in dimensions smaller than 4 and try to discuss the problem of emergent supersymmetry from the point of view of field theory. So now you should remember the original action and corresponding Lagrangians that I had at the beginning, with the potential and the Yukawa function. What you can do in 4 minus epsilon dimension, you can do it in any dimension actually. You can define dimensionless renormalized quantities. In this case denoted as lowercase u and lowercase h for potential and Yukawa function respectively. And you can compute the perturbative renormalization group in an epsilon expansion. And so what I'm displaying here is the leading result written in a functional framework. If you are more accustomed to beta functions of decoupling, we will see them in a few slides. So this is the leading order 1 loop RG flow in 4 minus epsilon dimension for these 2 guys. And for the specific model, which is this one, in which you have one scalar field and one Weil field, there is a hint already of supersymmetry in that if you compute the leading contributions to the anomalous dimensions of the 2 fields, actually they are the same, which is obviously a necessary condition if you want to combine them in the same supermultiplet, and they only depend on the square of the Yukawa coupling. Similarly, I can also define a renormalized superpotential in, again, the superpotential of superspace. And similarly, it has a leading perturbative RG flow. In this way, the first terms are just scaling terms, and the most important parts are these ones. And the anomalous dimension is also related, in this case, to the superpotential. Now, these two flows that I was showing, the one of the Yukawa and one of the superpotential, are known in full generality at 2 loops and with some assumption. In this case, they're known probably at 4 loops. Now, you can check explicitly that there is consistency between the two flows for a supersymmetric solution as the one that I was showing you at the beginning. So if I impose that the potential is the square of the first derivative of the superpotential and the Yukawa function is the second derivative of the superpotential, you can explicitly check that the beta function of the potential in this specific limit is related to the beta function of the first derivative of the superpotential, and the beta function of the Yukawa function is also related to the beta function of the second derivative of the superpotential. And the two RG flows are properly consistent, if you want, for leading order and next to leading order, which we checked in perturbation theory. Actually, we checked it in a little bit more generality. If instead you're accustomed to functional RG, you can think at these two flows as being consistent up to irrelevant operators. If you have a functional interpretation of the RG, like many of us do. Now, what is this SUSY fixed point? I just wanted to show you how it looks at this order in the next to leading order in the epsilon expansion. You can take the potential, express it, the superpotential, express it as a cubic interaction. You have a coupling lambda. The coupling lambda is an epsilon expansion at a fixed point. You can determine eta. And the one important feature of supersymmetry is that you have a super scaling. In this case, I would call it super scaling relation, which connects, if you want, the critical exponent nu of the correlation length and the anomalous dimension. And if you want to see it from the point of view of the CFT, of the super conformal field theory, you would say that the operator phi square, superpotential square, is a super descendant of the operator phi. And so once you determine eta, you also determine nu, at least if you are preserving supersymmetry. Now, the idea of the paper that, of 2017 was that we wanted to reinterpret a Yukawa system as a broken supersymmetric system. So essentially, we were manipulating it in such a way that we were writing the Yukawa function as a deviation y from the supersymmetric part, which would be just the second derivative of the superpotential. So the Yukawa system now looks like a supersymmetric system plus deformation. And there are several ways to do this, to break supersymmetry explicitly. And this was the one that we found the simplest to work with, but we tried others. And what you can do is you can compute the RG of this system. And now if you do, you're sure that when y is equal to 0, then supersymmetry is preserved. And so we were essentially showing that the perturbative RG of the Yukawa system can be written as the one of a broken supersymmetric system, provided you include some additional terms to the running of the superpotential. And here I'm displaying it in terms of the superpotential and the function h instead of the function y, just for convenience. But this is naturally, let's say, written in terms of y. And in fact, the additional term, if you essentially substitute h equal to w double prime plus the Yukawa term, plus the supersymmetry breaking term is essentially proportional to the supersymmetry breaking term. So we know that at y equal to 0, the system is respects supersymmetry. Now, the non-local term is essentially generated by the presence of these diagrams in which you have the F field and the phi field propagating versus the one of the Weil field. And if you are outside, if you have broken supersymmetry, these two diagrams don't cancel out. So you are essentially producing new phi to the 4 interactions in the super action, which are not good from the point of view of supersymmetry, but of course here we are breaking it. And I'm telling you this stuff because the general formula of the RG steps, as we essentially already discussed, is that for a supersymmetric action, an RG step for example, in dimensional regularization with scale mu preserves supersymmetry, which is essentially the first line. So we know that these two coefficients must be related and preserve supersymmetry. Here it's expressed in the traditional, let's say, space-time instead of superspace. But if you have broken supersymmetry, or if you're working with a scheme that does not preserve supersymmetry for some reason, what you can guess is that an RG transformation generates 3 terms. Okay, here parameterized with functions A, B, and C. So we have 3 terms, and previously we had 2. Of course, these 2 were related, so they had to be mapped into a single function. But now, if you have broken supersymmetry, I would like to attribute this function, the functions A, B, C, to the running of W and Y. So I have 3 quantities to attribute to the running of 2, which is something difficult and to think of. And our idea was that we should redefine the auxiliary field along the flow. The reason why we do that is that the auxiliary field stops being auxiliary if you are breaking supersymmetry, and your, let's say, RG step is giving it dynamics by accident. So our idea was that we should add, together with the RG flow, we should, through the RG flow, redefine the field F. The field F has its own beta function, which we insert in by hand. And we choose it in such a way that those 3 terms that I was showing you before become 2. And I can unambiguously attribute the 3 functions A, B, C to the running of the superpotential and to a combination of the running of the superpotential and the supersymmetry breaking term. So this was essentially the idea that we had. And with this idea, I'm not showing you all the details, but you can essentially use non-perturbative methods such as the FRG to study a broken supersymmetry flow. And some numbers in the equal to 3, you would think that the equal to 2 maybe would be more interesting for the proposals, but this is what we produced at the time. I updated the table a little bit with more recent results. And the first 2 columns are essentially the FRG results that we were producing. And I would take the Padere summation, which are the 3rd and 4th column, as the reference point at this stage, even though conformal bootstrap is moving on to address the situation. I wasn't really sure what numbers to include in the conformal bootstrap. So let's just take resound for loop Padé as benchmarks. And what is interesting is that the FRG, I mean, this is an unoptimized result in the language of FRG. So we could have done some more work improving it. But if you kind of average the 2 FRG results, you are close to the resound Padé. So which is a good signal. And obviously the FRG result is in need of improvement and it should be done in the future, certainly using the approach that I was suggesting in the previous 2 slides.
Omar, you 5 + 5. Okay,
thank you. So let me keep it very brief. Now, emergent supersymmetry has given me, let's say, the perfect excuse to study supersymmetry, even though it is decaying in interest from the point of view of particle physics. And now I want to show you some more recent result done in collaboration with Ori, which you can also see in the poster. So we decided to enhance the RG that you have seen before from one superfield to NF superfields. And the tensor, the superpotential W in this case has not only one coupling, but it has a tensor-like coupling, which is lambda ijk, and ijk are indices over this number of flavors. And since you have a cubic superpotential, you can infer already that there is a structural similarity with the Li-Yang and Landau-Potts field theories, which are renormalized generally in 6 minus epsilon dimensions. But this is not in 6 minus epsilon, this is in 4 dimensions, 4 minus epsilon. And it corresponds, if you integrate over superspace, it corresponds to an interacting Yukawa model with NF scalars and NF fermions, and a special relation between the potential and the Yukawa function. And let me try to cut the story short. The RG flow, of course, is richer than the single coupling case because you have indices in the tensor coupling, but it can still be written as a gradient flow with a trivial metric, at least at next to leading order. So there is a function A from which by taking one derivative with respect to the couplings, I can obtain all the beta functions. And so since you have couplings with an index, so tensor-like couplings, you can imagine that even though the general rotations in field space are not symmetries of the superpotential, the group of rotations is the maximal symmetry that it can have. Actually, is always broken by the fact that the coupling has 3 indices. But besides that, the group of rotations of the field induces an action on the superpotential trivially by rotating the field. And so, since we have an action of O, the group of rotations, I can decompose my tensor coupling into irreducible representations of the rotation group. So the tensor coupling is expressed as a vector, O and F vector, and then O and F3 tensor with traces equal to 0. So in the case of an F equal to 3, this would be 10-dimensional representation. There are 10 independent couplings written as the sum of the 3 and 7 irreducible ones. And with these tricks, we could study in general solutions for flavors up to number of flavors up to 3. And this is a general result, which does not assume any symmetry. But the outcome is that every solution that we find for NF equal to 1, 2, and 3 has a certain, let's say, in a way, emergent symmetry. And now, a lot of them are not maybe particularly interesting, but a couple were, let's say, catching my attention. And for 2 flavors, we noticed that one of them has Z2 symmetry. So I was thinking about claiming a price, which was a price given by Richkov and Sturgeon in a 2018 paper, and in which they were essentially giving a bottle of champagne to whoever finds a Z2 symmetric scalar theory, perturbatively unitary in 4 minus epsilon dimensions with more than 1 scalars, because otherwise easing would apply. And my idea was to take our model for NF equal to 2 and just integrate away the fermions. So this action is a purely scalar action, even though it has a non-local potential, let's say. Maybe I will claim this price together with Ori. And the other family of solutions that was catching my attention was that we can construct, in general, permutation invariance family of theories for arbitrary number of states of permutations. This would be a generalization of the Landau-Potts universality class. And unfortunately, we were not the first one thinking about it, because Rong and Su were also publishing something in relation to that. So the conclusion is that supersymmetry may be not observed at LHC, but it's a realistic possibility to observe it in a tabletop experiment. And personally, it has revived my interest in looking into Yukawa systems. And another conclusion, which needs some more work, which is what I was showing you at the end, is that there are potentially interesting families of Yukawa models in 4-epsilon dimensions, which are supersymmetric, but also have enhanced symmetry groups for more than one flavors of supersymmetry. So thank you for listening.
Thanks, Omar. That's excellent. Thanks for a very good view on supersymmetry and the applications, and so I would say the real world rather than the global. So I've got questions. Okay, Lucas first. Lucas, go ahead.
Yeah, thanks. I do have a question. So my question is actually, is this NF equals 3 generalization? How many supersymmetry generators does it have?
The number of supersymmetry generators remains the same, but you are multiplying the number of, so there are more super fields.
So does it mean it's still n equals 1 SUSY, or is there just one or how many? I mean, this. Can you go back to this table where you showed some anomalous dimensions as function of NF or some other?
Yes.
This one, precisely that one. So NF equals 1. That's the old model that you also discussed in the first place, right?
Yes.
NF equals 2. That looks as if it were I mean, at least the first line of that looks as if it were n equals 2 SUSY. Is that correct, or is it a wrong interpretation? I mean, this value of 1/3 is precisely the value that you get for the n equals 2 SUSY.
I believe you're right, because the special case S3, yes, the special case S3, but only that specific case. So if you have a permutation of Q states and there are states, this is n equal to 2 supersymmetry. So it's in this specific case, the number of superfields transforming with one supercharge combine into the one with the 2 supercharges. I believe this is also discussed in a paper. But so the inner reference inside the paper by Rong and Su.
But all the other examples are n equals 1, or?
Yeah, these are all n equal to 1. I assume that if there is, for example, an n equal supersymmetry, let's say equal to 4 norms, it will somehow appear later on. Because these are all scalar, so these are all chiral superfields with one real scalar.
Okay, thanks Omar.
Okay, Holger, you got your hand up.
Yeah, thanks, Omar. So for the symmetry to qualify as emergent, like supersymmetry, what would be relevant for me is that those operators or RG directions that violate the symmetry die out in the course of the flow. So now if you put more and more fields, you can also have more and more directions, more and more operators. Do you see a pattern that tells you that the symmetry can still be emergent in the sense that you put more operators, but they still die out towards the long-range limit?
I think this is a good question, and we're still studying it, so I wouldn't be able to answer properly. But there is one point that I want to make. So this type of analysis, so I'm not able to answer. I probably yes, but I don't know for certain. One point that I wanted to make is that this type of analysis done, for example, for the 504-like theories by Osborne and Sturgeon, reveals that if you consider models with an F greater or equal than 4 or 5, I don't remember, there's no absolutely stable. So in the general, from the point of view of the general couplings with no symmetry, there is no absolutely stable infrared potential. So all potentials, all fixed points have at least one irrelevant direction. So this is to say that from the point of view of the RG, UV, and IR are just completely arbitrary. And as you say, we need to somehow protect. We need to somehow complement, let's say, the stability analysis with a degree of symmetry to have an emergent solution.
Okay, so last question from Andrea, then we move on.
Omar, so this model for NF going to infinity can be solved analytically. Do you see a pattern evolving if you increase NF that goes towards this limit, or, you know?
I believe that if you want to take NF to infinity, you have to choose which a family of solutions. For example, if you take the permutation symmetry, which is a function of an F, and you can take the number of infinity, or I believe that there is an O and F minus 1 family, and you can take an F to infinity there, but I can't take this table because this table just keeps growing.
Well, actually, in the infinite n limit, you have a one-dimensional submanifold of fixed points. So we have infinitely many fixed points.
I think there is always some implicit assumption, but in my experience, what happens is that, for example, if you take S and F, and you go to an F infinity, then you get a decoupled, in the case of the Ising, you get a decoupled Ising model. So in this case, you will get a decoupled model, so n copies of, many copies of the first one. So, but this is not guaranteed. There are always some hidden assumptions in these limits. And you have to be careful.
Okay, so I think we need to move on. Thanks, Omar, for an excellent talk.
Thank you.
And so if you could release the screen. And then, so David Shaik from Liverpool is the next speaker, who's going to continue the supersymmetry theme, but in 3 dimensions Yang-Mills. So thank you, David.
Thanks very much for that introduction and also for the invitation to speak at this workshop. I'm going to assume that I'm audible, the slides are visible, as well as the pointer as I move it around. And I'd just like to say that as we come to the last day, I've really been enjoying seeing how all the various different topics and approaches that people are working on are being brought together in this focus on 2+1 dimensional theories. And I'm glad to be able to add yet another topic to that in the form of lattice studies of supersymmetric gauge theories that have supersymmetry built in at the fundamental level of the microscopic theory rather than an emergent property. So yet another topic encompassed in this very diverse program. So these studies, specifically in 3 dimensions, are ongoing work with the most recent results coming out last autumn in collaboration with Simon Catterall, who's speaking later today, Joel Geet, Raghav Jha, Angel Sherlotov, and Toby Wiseman. And even that three-dimensional case is just a component of broader investigations of lattice supersymmetry that at this point have touched on all levels of dimensions from 0+1 dimensional quantum mechanics up to 3+1 dimensional space-time that we live in. And of those, I guess the main theme that I want to emphasize in this presentation is that the 2+1 dimensional case is a really promising one that offers possibly the best balance between the richness of the physics that we have to look at from these lattice calculations, while at the same time controlling the computational costs that are necessary to go into these investigations of supersymmetric quantum field theories, which operate quite differently from the more traditional QCD-like theories. So what I'm going to do in this talk is just review a bit of the motivation for supersymmetry, and in particular supersymmetry on the lattice. There will be some definite echoes of what Omar was just presenting. And then just some highlights of the lattice formulation that we work with, which will have to be just highlights in order for the talk to finish in the time available. And I'll need to go through those quickly and not be bogged down, but at the same time, try to provide enough information so that the results that come at the end will still be comprehensible, looking at various supersymmetric theories that I will define in more detail as we approach them. And I will just say, in terms of logistics, you can get a copy of these slides online with the link that should be in the chat window. With my setup, I can't see the chat window, so while I encourage you to interact and interject if there are any questions that come up along the way, do feel free to say those out loud or let me know if there is a question in the chat window for me to be aware of. But moving on to the motivation, I think I can go through this quickly because it is quite similar to what Omar was saying, that while supersymmetry is best known to your innocent bystander as a potential extension of the standard model of particle physics, when we go down into 2+1 dimensions, that becomes less relevant, and we're really more interested in other aspects of supersymmetry as really just a symmetry, which simplifies the complicated dynamics of quantum field theory. And in particular, over the past 25 years or so, in round numbers, supersymmetry has really been crucial to driving progress in detailed understandings of properties like conformality, confinement, dynamical symmetry breaking, and dualities in quantum field theory. And just focusing in on dualities for a moment, these include two distinct classes, both dualities between different gauge theories, different quantum field theories in flat space, so-called Seiberg or electric magnetic dualities. But there's also a special class of dualities that are deservedly famous, known as holographic dualities, that relate these supersymmetric quantum field theories to quantum theories of gravity, typically based on string theory, but secretly the same physics, the same dynamics as the supersymmetric systems formulated in flat space-time. And what we want to do with lattice calculations is introduce another tool well suited for the strongly coupled aspects of these supersymmetric quantum field theories, to analyze them and to gain more insights than can be obtained through exact methods or perturbative calculations. Now, it should be clear by this point in the talk that of the various communities represented in this workshop, I'm coming from the lattice field theory side of things and also the particle physics side of things, where we are introducing a lattice structure to space-time as a way of regularizing the path integrals that define formally the observables we want to compute or predict for these quantum field theories. So formally, these are infinite dimensional path integrals over all of the degrees of freedom in the system. The lattice approach regularizes the systems by formulating the theory in a finite, discrete Euclidean space-time, which has some nice properties in terms of being a gauge invariant regularization, which does not rely on perturbative expansions and operates directly in the D dimensions of interest. And I actually got a notification that a hand has been raised. So let's take that question now before getting further away from what raised it.
I think it was an accident.
I'll move on then. But with any regularization of a quantum field theory, there are always challenges or imperfections to deal with. One that will be quite relevant in this context is that the finite distance or lattice spacing between nearest neighboring lattice sites is introducing a UV cutoff. This is somewhat similar to just a naive cutoff regularization, but the lattice structure is smarter than your average cutoff in the sense that if the lattice is sufficiently regular, it preserves some discrete subsets of the continuous space-time symmetries like the Lorentz or Poincare invariants, and this is sufficient to guarantee that those continuous symmetries are automatically recovered when we remove this UV cutoff by taking the continuum extrapolation, sending that lattice spacing to 0 with infinitely many points infinitesimally close together. Now, the breaking of Poincare invariance is extremely relevant for supersymmetric quantum field theories because, as Omar just nicely reviewed for me, supersymmetry is a space-time symmetry, extending Poincare invariance with the addition of these spinor generators whose anti-commutation relations generate infinitesimal translations necessarily broken in discrete space-time. So the supersymmetry algebra itself is broken at the classical level, and in a lattice quantum field theory calculation, this opens the door for all sorts of relevant supersymmetry violating operators to appear as quantum corrections that would then have to be fine-tuned away in order to recover the theory of interest in that continuum limit. And these include masses for scalars, for quarks, gluinos, Yukawa couplings, and for scalar quartic couplings. And over the past 10 to 15 years, we've really been able to progress this field by finding a way to preserve a subset of the supersymmetry subalgebra, even in this discrete lattice spacetime, in order to ensure the correct continuum limit with much less fine-tuning than would naively be required, and in some cases, no fine-tuning at all. This is background that I don't have any time to talk about. There are equivalent constructions from orbifolded dimensional deconstruction as well as so-called topological twisting that was reviewed in this work about 10 years ago. And I'm going to be going through a brief summary of the topological twisted approach. But in both of these approaches, we need a sufficient amount of supersymmetry in order to be able to preserve a subset of it on the lattice. And in particular, 2 to the D supercharges have to be present in D dimensions. So looking at the 3-dimensional 2 + 1 dimensional theory, we have 2 options of the, what I called earlier, the half maximal case with 2 cubed is 8 supercharges, or the maximal case of 16 supercharges, which is the one that I will go through briefly in terms of the formulation, the how we are carrying out these lattice calculations. And I personally find 3-dimensional maximally supersymmetric Yang-Mills theory easiest to understand as the dimensional reduction of the 4D theory, so-called N = 4 super Yang-Mills, which has already come up in some of the earlier talks at this workshop. This 4D theory is a famous testing ground for things like dualities, S-duality, ADS-CFT duality, where it is the CFT of Maldaceno's original work on scattering amplitudes, and even more theoretical investigations. It's arguably the simplest non-trivial field theory in 4 dimensions, which involves a gauge field plus 6 scalars with 4 component fermions accounting for the 16 fermionic degrees of freedom that correspond to those supersymmetry charges. And all of those fields transform under a global symmetry that's called an R symmetry for obscure historical reasons, and taking a dimensional reduction of this theory shifts a bosonic degree of freedom from the gauge field that now has 3 components. The last component of that becomes a 7th scalar, and the different spinor algebras from 3 to 4 dimensions give us so-called n = 8 2-component fermions, still with the same number of supersymmetries in the maximal case, and a larger R symmetry that contains the SO4 subgroup, which is all that we will need for the construction. And if we look at the Lagrangian that I won't write down here, there are all the usual kinetic Yukawa quartic terms. But because there are all these symmetries, both supersymmetries and R symmetries, all of the coefficients of those terms are related to each other so that they only depend on a single 't Hooft coupling lambda, which is the Yang-Mills coupling G squared times the number of colors N in the gauge group. In 4 dimensions, what I find intuitive about this setting is that the topological twisting can be viewed as taking those 16 supersymmetries, putting them into a 4x4 matrix, and then expanding that in a basis of gamma matrices, so that the 4x4 16 supersymmetries are recast as 1 + 4 + 6 + 4 + 1 calligraphic Q, the so-called twisted supersymmetries, which I can recast into these 1 + 5 + 10 twisted supersymmetries with indices ranging from 1 to 5 rather than 1 to 4 for reasons that will become clearer in the next slide. And all of these multi-component tensors are anti-symmetric, which is how the counting comes out correctly. And what's going on here is just a change of variables. It's not affecting the physics at all, but we are casting the fermionic degrees of freedom and the supersymmetries in representations of the so-called twisted rotation group, the diagonal subgroup of the direct product of SO4 Euclidean rotations, once we've done that Wick rotation into Euclidean space, with an SO4 subgroup of that global R symmetry. And in particular, in discrete space-time, this scalar supersymmetry is essentially the square of, or it is a linear combination that squares in the anti-commutation relations 2 infinitesimal generators that loop around a closed circle. They can be located just at a lattice site, and that lattice site can be taken to be just a single site rather than a translation in space-time, and hence preserved exactly on the lattice. And then taking this construction down from 4 dimensions to 3 dimensions, we again reshuffle the fermionic degrees of freedom from reducing that final dimension. So we get back from 1 + 5 + 10 supersymmetries to 1 + 1 + 4 + 4 + 6. So 2 scalars, 2 vectors, and 1 antisymmetric tensor, where the twisted rotation group is now based on the direct product of the SO3 Euclidean space, an SO3 subgroup of that global R symmetry. And there are 2 scalar supersymmetries that we can preserve at non-zero lattice spacing. Now, the fields of the theory, the gauge fields, the scalars, and the fermions also have to be recast in terms of representations of this twisted rotation group. And I guess in the lattice context, and for the lattice experts in the audience, a feature of this can be appreciated that these are all being turned into integer spin representations of this twisted rotation group. There are no spinners left, which is pleasing to hear for a lattice field theorist, because we know that spinners tend not to play nicely with discrete space-time. And this is in some sense, the essence of how this twisting approach helps us improve the situation with these supersymmetric quantum field theories. So the fermionic fields that we have, again, in 4 dimensions get recast in the same way as the supersymmetries themselves. A twisted scalar fermion eta, twisted vector fermion psi, and antisymmetric twisted tensor fermion chi. And for the gauge field and the scalars, these add up to 10 bosonic degrees of freedom, and they get recast into actually complexified gauge field A and A bar, again with these 5 component indices, where the complexification of this gauge field implies that the gauge theory we're working with in the lattice calculation is not just the SUN of the target continuum theory, but is enhanced to a full UN theory that in the continuum just trivially decouples into SUN and U1 sectors, which is not the case in a lattice calculation. We'll come back to that in just a bit. But with this twisted formulation, it's a fairly straightforward exercise to check that the single twisted scalar supersymmetry in 4 dimensions is correctly interchanging bosonic and fermionic degrees of freedom. So the supersymmetry acting on the gauge field gives us that vector fermion with all the same indices and representations acting on that gauge field again with the supersymmetry squares to 0 going across each line here. It all works out that same, where this D is that bosonic auxiliary field we also saw in the previous talk, necessary to keep the supersymmetry closed off shell without imposing the equations of motion. And again, going down to 3 dimensions, this 5 component gauge field is reduced to 4 components with 2 extra scalars coming from that 5th component being realized there, and all of the supersymmetry continuing to operate as it should. And with that setup, the shift from continuum field theory to lattice space-time is almost trivial, not entirely, but it looks quite the same despite breaking all of the supercharges that have these twisted rotation group indices, the vector and tensor supersymmetries. We just have to replace the gauge covariant derivatives with finite difference operators connecting nearest neighbor lattice sites, and the complexified gauge fields get mapped into gauge links, which, in contrast to the usual approach to lattice field theories like QCD, live in the algebra, GLNC, rather than in the group itself. But the supersymmetry transformations still work out the same, and there's a nice, geometric interpretation of these fields where the scalar fields are identified with lattice sites, the vectors are identified with the links, and so on. And it's straightforward to see that the lattice action that we get in the same form as the twisted continuum action is supersymmetric in the sense that acting on it with this twisted scalar supersymmetry produces a vanishing variation. Now, the one last wrinkle to go through here with the formulation before moving on to results, actually there are 2, but this is one of them. We have these D+1 links in the D-dimensional theory. So the 4D theory for n = 4 super Yang mills has 5 component objects that get reduced down to 4 component objects for the 3D theories we're looking at. So they all have to be formulated on so-called 80 star lattices, which are in 2 dimensions, that is just the triangular lattice. We can count that there are 3 links going around the basic unit cell of this lattice. And that, since it's in 2 dimensions, these basis vectors are necessarily linearly dependent and non-orthogonal. But the large SD+1 point group symmetry of these lattice structures is crucial to recover the twisted rotation group in the continuum limit. The representations of that point group symmetry that the lattice fields transform under map smoothly onto the representations of the twisted rotation group in the continuum limit. And it's precisely that recovery of the twisted rotation group that promotes the recovery, the automatic recovery of all of the other supersymmetries in these theories that are broken by the lattice discretization, thanks to the preservation of that subalgebra of the supersymmetries. Now, this is a very nice formulation. Unfortunately, you can't use it for numerical simulations just because it has the same zero modes and flat directions that are features of the continuum theory and must further be regulated in the context of a calculation that we want to carry out on a finite computer. And these actually become especially challenging in that U1 sector of the complexified gauge group that you don't have to worry about at all in the continuum context. So just to quickly go through some of the final details of this lattice formulation, in the numerical lattice calculations, we have to add a handful of deformations to the theory in order to get it to run on the computer that we then remove in the process of taking that continuum limit and recovering the quantum field theory of interest. The first of these is just a simple potential for the scalars that lifts their flat directions. And since it only involves the scalars and not the fermions, it's easy to appreciate that this is a supersymmetry breaking potential being added to the lattice action, where the key is that this is a soft supersymmetry breaking. So all of those relevant operators I warned about earlier are generated with coefficients that are proportional to this tunable parameter mu squared that controls the size of the scalar potential. And if we measure the violations of the supersymmetry by, say, computing violations of word identities, supersymmetry variations of operators that should vanish if the supersymmetry were exact, we can confirm that all of these word identity violations depend linearly on this deformation parameter and vanish, go to zero, as we tune that parameter to zero, which becomes an ingredient in our continuum limit, our continuum extrapolation. Now this, because it involves the complexified gauge length squared, is only sensitive to the SUN sector. U1 phases cancel out between that U and U bar. So we have to add a second deformation to constrain an object that depends on the U1 degrees of freedom. This comes from the plaquette, the elementary face of the lattice, and in particular its determinant is a simple object that is sensitive to that U1 sector. And here we have had great success formulating this deformation supersymmetrically by modifying the auxiliary field equations of motion. And again, this is the same sort of plot as before, only now on log-log axes, looking at the continuum limit of the lattice spacing A over the lattice size going to zero, and showing two different formulations, one in which this plaquette determinant is constrained with another simple supersymmetry breaking potential. Those are the red points, and the blue points come from this supersymmetric implementation. Both of these are actually going to zero in the continuum limit. One is just going to zero with a slope of 2, so like a power of a squared in this log-log plot. The other with a very nearly logarithmic decrease. So what we have achieved here is effectively, in the parlance of lattice calculations, an order A improvement of the lattice calculations through this improved action that includes this plaquette determinant constraint in a supersymmetric manner that is too complicated for me to want to go into here, though I can say more about it if there's interest. The final deformation only arises when we do a naive dimensional reduction to use our 4-dimensional maximally supersymmetric code to look at lower dimensional theories, whether that is in 1+1 or in 2+1 dimensions. What can happen here is that if we set the extent of one of the spatial directions of this code to just be a single site, we observed empirically that the would-be Wilson line going around that reduced dimension, which is just the trace of that scalar field that we pick up upon the dimensional reduction, can, or typically does, vanish. It becomes, this is the modulus of that Wilson line, so it's a non-zero value, but we see that there is effectively center symmetry breaking occurring in that reduced direction, which I'm getting a bit hand-waving here. What is going on, sorry, it's an absence of center symmetry breaking. It's a restoration of center symmetry in that reduced direction with adjoint fermions, which is something more like so-called Higuchi-Kawai reduction of lattice field theories rather than the Kaluza-Klein dimensional reduction that we want to look at in order to investigate these 2+1 dimensional theories from the 3+1 dimensional code. So adding this additional potential term, again, softly supersymmetry breaking, but we give it the same coefficient as the SUN scalar potential. This ensures that center symmetry remains appropriately broken in the reduced directions, and we get the target theory that we are actually interested in, which I will now start showing results about, just following a brief advertisement that all of the code for these calculations is publicly available on GitHub with a manual in computer physics communications, and an update to that currently being written and hopefully out later this summer or later this year. I expect, given the past 15 minutes or so I've been going through all of the features of the construction that we have to work with, it's not surprising that there's a fair amount of complexity in the code itself. And the idea of making this code all publicly available is to reduce barriers to entry for anyone who might be interested in checking out these supersymmetric quantum field theories on the lattice on their own. Now, moving now into some numerical results, the first set I want to look at deal with the thermodynamics of this maximally supersymmetric, the 16 supercharged Yang-Mills theory in 2+1 dimensions, which is formulated on a 3-sphere with dimensionless sizes, what we'll call R1, R2, and R beta, where R beta is the temporal extent where thermal boundary conditions are imposed. So a fermion going around that temporal cycle in this 3 torus picks up a -1 phase, anti-periodic boundary conditions, whereas a boson going around any of the 3 cycles is given periodic boundary conditions, and everything is periodic in those 2 spatial cycles. Due to the formulation of the theory on the A3 star lattice, this ends up being a skewed 3 torus, which introduces some complications I will spare you here. But what we're interested in looking at with this setting is the low temperature behavior of this theory for SUN gauge groups with a large number of colors n, which holographic duality relates to the behavior of black holes, or more generally black brains, in the holographically dual supergravity theory. The supergravity is effectively the leading term in the stringy quantum gravity that is really at play in these holographic dualities, where corrections are coming both from, say, higher order terms, quantum effects in the string perturbation theory that are controlled by the number of colors, and so-called alpha prime corrections, which is resolving the finite size of a string compared to point particle degrees of freedom, which are suppressed by having a sufficiently low temperature in this. That's what's being illustrated in this little cartoon by Toby Wiseman, where the horizon, the black brain that we are interested in studying is sort of located at the bottom of the so-called throat in this sketch of the dynamical quantum space-time metric drawn here. Now, even at those low temperatures and in the large N limit, this holographic duality is predicting a rather complicated, or I might call it rich, phase diagram being conjectured depending on the relative sizes of the temporal cycle of the torus that our theory is formulated on, compared to each of its spatial cycles, compared to the dimensional coupling in the three-dimensional context, which I realize I forgot to mention here. This dimensional coupling lambda in 3 dimensions is being combined with the dimensional temperature in order to make everything dimensionless as the inverse temporal extent of our 3 torus. Now, in some previous work in 1+1 dimensions, we actually took a look at the phase diagram conjectured by holographic duality, which is not surprisingly simpler in the lower dimensional case. Here, just as a first study, we are going to restrict ourselves to the simplest possible case, the so-called D2 phase, where everything is homogeneous and our skewed 3 torus has cycles of equal length in all 3 directions. And in the lattice context, this translates into a lattice volume L cubed, or an aspect ratio of 1, where the continuum limit corresponds to L going to infinity with a fixed dimensionless temperature that brings in the dependence on the 't Hooft coupling, where as the temperature gets lower, the lattice coupling gets stronger, but as the lattice size gets larger toward the continuum limit, the coupling gets weaker. It can be challenging to keep track of all of those factors, which is why I haven't tried to go through that here. But let me know if you want to review those details. The first thing to check at these low temperatures is to confirm that we are actually in the homogeneous D2 phase we want to target, where the homogeneity in the holographic duality context in the lattice calculation translates by this holographic duality into the behavior of the eigenvalues of the Wilson line around either of the spatial directions of the lattice, where homogeneous means that the Wilson line eigenvalues should be uniformly distributed around the unit circle, or in other words, the phases of those eigenvalues. If we plot them in a histogram as shown here, should just be a flat line for all phases from -pi to pi. And what we can see by comparing 4-color, 6-color, and 8-color field theories is that there is a steady approach to that desired uniform distribution as the number of colors increases, which is the domain where holographic duality is robust. And that gives us sufficient evidence to conclude that we are indeed in the correct phase and at sufficiently low temperatures to really look at the behavior of that supergravity cast through this holographic duality. And what we want to look at as a first observable is, in the lattice calculation, it is related to the density of the bosonic action of the theory, which, turning that through the holographic duality dictionary, corresponds to the internal energies of these low temperature holographic black brains. And there is an exact calculation in supergravity, which is a leading order expansion in the full quantum gravity calculation, that predicts that the energy of these black brains, the quantity that we're measuring, should depend on the dimensionless temperature to the power of 10^3, so 3 1/3, with a known coefficient of about 0.8. I hear what might be a question, so I'll pause in case it is one.
I can just interrupt, David. About 5 + 5 left.
That was what I was hearing at the prompt. So should be in good shape to wrap up. And what we can look here as this first result is that our lattice calculations are indeed approaching the black dashed line coming from this leading order holographic prediction for sufficiently low temperatures. About T less than 0.4, they are breaking away from the high temperature prediction that is coming just from counting the bosonic degrees of freedom in a high temperature expansion, moving away from that red line and towards the holographic prediction, especially when we carry out the continuum extrapolation of taking the lattice volume L cubed to infinity, that's shown in the right-hand plot. You can see that especially at the lower temperatures, that continuum extrapolation is moving the prediction away from the high temperature result and into even better agreement with that holographic prediction. So this is encouraging progress, not only to reproduce the leading order expectation at low temperatures, but using that as a base to really give non-perturbative or all orders predictions for how this system is behaving away from that holographic regime where the predictions of the duality can be trusted. And yeah, given the time left, I'll move quickly through the work in progress and some of the future plans, which is going from that maximally supersymmetric theory to what I called earlier the half maximal super Yang mills, where we have 8 supercharges. And this is something that we can't look at in a twisted construction at 4 dimensions, but if on the basis of all of the twisted formulation that we went through earlier, it's a bit easier to understand that now we take these 8 supercharges and recast them as integer spin representations of that same twisted rotation group in the SO3 twisted rotation group in 3 dimensions. There are 1 + 3 + 3 + 1 components here, corresponding to a scalar vector, and then 2 and 3 index antisymmetric tensors that when we take the theory and put it on a lattice, we no longer have to rely on that AD star lattice or A3 star lattice in 3 dimensions. We can just have a correspondence with a simple cubic lattice and fermions identified or associated with sites, links, faces, and the entire volume of the unit cube. Of course, the downside of having a different lattice structure, even if it is a simpler lattice structure, is that the existing code has to be rewritten essentially from scratch to incorporate the different lattice structure that we have. And this is something that Liverpool PhD student Angel Sherlatov has been doing over the past few months, where we have that code up and running and passing all the tests we've fed it through so far, so that larger scale calculations are getting underway. And what's shown here is just an analog of the word identity violations we were looking at earlier, where looking at a different and a simpler word identity here, where the violations are still at the percent level on a very small 4 cubed lattice, but still with the larger error bars that come from those quick tests, they're still decreasing as appropriate with the tunable parameter of that scalar potential that we have to put in to control this lattice calculation. And I really want to emphasize in the time remaining that the target that we are going after with this new code development is not just the super Yang bills itself, but also adding superfields to these systems. So these came up in Omar's talk, adding so-called quarks and there's superpartner squarks to the theory, which is necessary to investigate a lot of the interesting features of these supersymmetric quantum field theories, like those electric magnetic dualities and dynamical supersymmetry breaking, at the expense of more of these supersymmetry violating operators potentially reappearing and needing to be controlled with fine tuning. And again, in the same way as the supersymmetric Yang-Mills case that we have done in the past and are still working on now, we can avoid these fine-tuning challenges by preserving a supersymmetry subalgebra, even with these superfields added, with what is called a quiver construction that's based on this twisted super Yang-Mills, something that Simon Catterall and R.T. Vernala did some work on about 6 years ago, from where I've taken this illustration of the idea that we formulate a super Yang-Mills theory in d+1 dimensions with only 2 slices in that +1 dimension, and actually a different gauge group on each of those 2 slices, which is where the quiver terminology comes from. And if we turn off the gauge coupling on one of those slices, the gauge invariance becomes a global symmetry that we can identify as a flavor symmetry, where the fields on the links between those 2 slices that transform into bifundamental simply reduce to fundamental superfields that also transform in the fundamental representation of that global flavor symmetry. So we have F flavors of fundamental fields, both fermions and their superpartner bosons. So this was done a few years ago for the case of 3D super Yang-Mills with 8 supercharges being reduced to 2-dimensional super QCD. We're going to check that with a nice parallel code that Angel has developed, and then go from there to look at the 3-dimensional super QCD based on the 4D n=4 super Yang-Mills, benefiting from the experience of going through that simpler lower dimensional calculation. So that's all I wanted to show you today, just to emphasize some of the directions we are exploring on this frontier for lattice supersymmetry in 2+1 dimensions, where our initial results on the thermodynamics of the maximal supersymmetric Yang-Mills theory still leaves a lot of further directions to pursue, including that rich phase diagram we can look at. And there's work in progress on the so-called half maximal theory that will lead into supersymmetric QCD, and as always, keeping track of potential sign problems in these theories, which I can talk about if there is interest. But for now, I'll just thank you for your attention and see how much time may remain for any further questions before we head to that gather town.
Okay, thanks, Dave, for a very stimulating talk. I was a bit worried you had another 7 slides left, but that's a bit of a relief. I was wondering how
only if there was time remaining, which there is not.
Yeah, no, I was worried about halfway. Right, any questions? Let's see. No hands up yet. Okay. I think Lucas was in there first. Go ahead, Lucas.
Yeah. Hi. So, I mean, some of these, it's really nice that some of these supersymmetry generators you can keep exactly. Others are only kept in the, are only preserved in the thermodynamic limit, right?
It's even the continuum limit that is. So there are 2 possible thermodynamic limits that you can have in a lattice calculation. You can have an infinite number of sites with still a finite lattice spacing between them. But you do need, in the continuum limit, to keep a finite volume. You need that thermodynamic limit as a component of the continuum limit. And it's the continuum limit that is key to recovering the full theories. This is really analogous to how continuous rotational invariance is recovered in the continuum limit of lattice QCD, which is why I had that in the background.
Okay.
But
And so, okay, I see. So, but these are these plots where you basically plot some word identities as function of 1 over L or A over L, I guess.
yeah, so I can go back to that briefly and just clarify that this is a word identity for that scalar supersymmetry that is exactly preserved by the formal construction, but then has to be softly broken in order to regulate a lattice calculation. So this is the recovery of the subalgebra in the continuum limit. And then based on the recovery of that subalgebra, here it is, that in combination with the point group symmetry is what guarantees the restoration of all of the other supersymmetries that are necessarily broken by the discretization of spacetime.
I see, I see. So is it possible from these plots to extract some scaling dimensions of these operators? At least in principle?
Not from those plots. So the scaling dimensions, I've only looked at scaling dimensions in the 4-dimensional n=4 theory, and I've kept all of that out of the background here. So we have some results and proceedings for the scaling dimension of what's called the Konishi operator, which is sort of the simplest operator in n=4 super Yang-Mills. It's just 2 scalar fields. And there are a bunch of methods that we have used to look at that, just looking at power law decay of correlation functions, looking at what's called MCRG, Monte Carlo renormalization group calculations. There's a stability matrix there, and also finite size scaling. Have not looked at any of that in 2+1 dimensions yet. That's still a frontier. You know, these maximally supersymmetric theories are believed to flow to conformal fixed points in the infrared. And it's more future work just to confirm that we can see that, which is challenging even in non-supersymmetric theories on the lattice. And then based on that, scaling dimensions would be a next step, nothing that we've started yet.
Okay.
It is sort of on our minds for the far future, and certainly interesting.
Yeah, okay, thanks.
Okay, Simon, you're up next.
Just a quick question, David. Your results for the black brane energy, you're kind of moving towards the expectation of the 10^3 power, but you're not there yet. Do you have any idea of how close you need to get to the continuum limit, or how big a lattice you need? And I guess really I'm asking what resource do you need to get there?
So it is a simple question with a lot of directions I could take the answer. So one shortcoming of the plot on the left I'm showing here is that the different colored points are the different lattice sizes without the continuum extrapolation. And for the sort of 4 points in the middle there, the continuum extrapolation is actually flat within the error bars that we have on the right-hand side. But if I were to show the continuum extrapolated values of the lowest 2 temperatures, those would actually be there. They would be in agreement with this leading prediction, again within relatively large error bars at the relative level. So the 2 quantities that we have to play with here are the lattice size L and the number of colors, the gauge group SUN or UN, technically in the lattice calculation. And both of those are, we always want to do larger numbers of colors on larger lattices. And it's easier for us to increase the lattice volume and use the parallelization of the code to spread that out around more processors. So this is getting up to 16 cubed volumes, and it would be straightforward on existing resources to double that in all directions, get up to 32 cubed with this 8-color gauge group. The number of colors, the naive computational cost for matrix multiplication increases like n cubed. So n=8 is already 20 times more expensive than the n=3 that QCD would have, and that's a bit more challenging to increase. So what I expect to be sort of the next step to get the continuum extrapolation more precise here is going up to 20 cubed, 24 cubed, and maybe even 32 cubed lattices, which are going to have smaller error bars from the better self-averaging, as well as getting closer to the continuum limit, and then smaller error bars on those extrapolated values for a more precise comparison with that dashed black line. And all of that is not really going to be a challenge in the computing side of things. The challenge is more on person time to manage those, given the small number of us working on this compared to some of the lattice calculations and the large number of other projects that we all have going on at the same time. I see another hand came up while I was going through that. I don't know if there's time
to do it.
Yeah, I'm happy.
Okay. Okay, Joseph, this will be the last question for the gather then.
Okay, yeah, I was wondering, so in your formulation, you exploited the fact that your lattice action preserved this kind of scalar SUSY generator Q, which is a generator of the algebra. But I was wondering whether more generally, let's say if you had a cubic spacetime lattice, whether that could preserve like a discrete subgroup of the full Poincare group, right? A bit like, if we look at it doesn't matter if we have a Hamiltonian on a cubic lattice, then it will preserve the OH cubic group. And then it's a big
Yeah. No, this is an excellent question, and was a famous, one of the earliest works in lattice supersymmetry from, I believe, 1976 by Nicolai and Dodondi was looking and investigating exactly that question. Can we define, say, a discrete supersymmetry in a lattice spacetime based on a finite difference operator that we have there? And the answer turns out to be no. And this has to do with something a little more formal than I went into in this presentation, the Leibniz rule in discrete spacetime, which has to be preserved in order for the full supersymmetry, or in order for a supersymmetry to be formulated. And there are no-go theorems developed over the past 15 years or so, showing that any finite difference operator in a discrete spacetime that obeys the Leibniz rule and can be used as a formulation of supersymmetry along the lines you're suggesting is necessarily non-local, and that has its own challenges to work with. There is ongoing investigations of this, mostly in 0+1 dimensional quantum mechanics, but the constructions become quite complicated quite quickly, and also tend not to work for gauge theories in any event. So that is an excellent question, where there's a lot that can be said.
Okay, thanks very much.
Thanks, Joseph. So I think we'll just close it there for this session. Thanks again to David and Omar.